still understand that it's just a definition. Okay, that simplifies things. We don't have to do the math. Now the Jacobian times we now have that c point is equal to 0, and that is the Jacobian times the first time derivative of OM of our state vector, and that, well, basically let's call it u or something. Okay, so the Jacobian times the first time derivative of s is equal to 0, which means that its derivative is equal to 0, and that's by the chain rule is equal to g points times the s points plus g s2 point. Now, what do we have according to Newton's law? Well, m s2 point is equal to f plus fc. That is the forces that we know the expression of, and fc is basically the forces that we don't know. In this case, fc is just t and f is just p. Okay, this means that s2 point is equal to w f plus fc, where w is the inverse matrix of m. Of course, m, as I said, is inversible since it does not contain any zeros on its diagonal, since there are no zero masses. Now, if we write this down, we should take this expression, plug it in for s2 points. You get this expression, g points u. As I said, u is just s point, and then you get this expression, g points u plus g wf plus g wfc, and then we are interested in fc, so this is the unknown. We take it to the this term to the other side, and we get this. Okay, let's try and apply this equation to our system that we're studying, the simple pendulum in 3 dimensions. So the constraint is x squared plus y squared plus z squared, and s is just x, y, z. Note the difference between the column vector and the row vector. It's really important. I mean, if you want to make a column vector a row vector and vice versa, you should take the transpose. There is some basic linear algebra stuff you need to deal with to calculate these things. So j is just the derivative of c with respect to s, so you take the partial derivatives, as I said in the definition of the Jacobian. So it's just 2x, 2y, and 2z, because partial derivatives, you take y as a constant when you derive with respect to x or z, and vice versa. So g point is just going to be 2x point, 2y point, 2z point. You take the time derivative of each component, and then the force is 0, 0 minus mg, where g is just the scalar 9.81. And w is just going to be 1 over m, the identity matrix, since we don't really have a system of particles, since all these terms are non-existent. The term is the only one. So just the identity matrix just goes away in our calculations, and then, well, we plug in this equation. So this is Jacobian, and this is the force. The force that we want to know has 3 components: fcx, fcy, and fcz. So these are our 3 unknowns, -2, etc. You just plug in everything according to this, and then you have this. Well, this is a matrix 1 by 3, and this is a matrix 3 by 1, so its products will be just a 1 by 1, which is equivalent to a scalar, basically. So this will give you 2x fcx plus 2y fcy plus 2z fcz over m, and this will also be equal to a scalar. Now this is a scalar equation, and we have 3 dimensions in fc. We have 3 unknowns, fcx and fcy and fcz. So we clearly lack something. We cannot really solve 3 unknowns with 1 scalar equation. It's impossible. We now introduce, to solve this problem, the principle of virtual work. The force that the system applies to keep a constraint satisfied for all the time will be the force introducing the principle of virtual work. Now, the force that the system implies on our particle to keep a constraint satisfied shouldn't add or remove energy from the system. In other words, its power should be 0, and that's completely natural. I mean, it should be perpendicular to the velocity, first of all. that means that the scalar product is 0, and that means that the power is 0, and power is the time derivative of energy, so yeah, all of that. Or it's clear that if you give some initial energy to the system, this energy should be changed. The system shouldn't add energy from itself. Then we are creating energy, and that violates the second principle of entropy and of thermodynamics. Entropy is always ascending. So we have the power is equal to 0, which means Fc scalar products with V is equal to 0, and that means that V, since V is just dom over dt, dt is non-zero, so you just take it out, and then Fc dot dom is equal to 0. Now, we need to find another condition on Fc to solve this problem, since we have one scalar equation. So we just impose this condition. Now we know that the differential of a function is just the sum of the partial derivative with respect to a component times the elementary displacements on this component. This is some math stuff, and that means that, well, the differential of a function is just, it's Jacobian times DOM, and this is by definition it. I mean, as I said, J is just the derivative of a scalar function with respect to its components. Yeah, it's just there. This is the derivative of the Jacobian. So it's normal that d of f is just j times dom. Now, we want this to be equal to 0, since our constraint should be always a constant, so its differential should be equal to 0. So the only vectors that, such as their scalar products with DOM is equal to 0, are the Jacobian, or in other terms, the Jacobian times a constant, since a constant doesn't change anything. Lambda times 0 is just 0. So Fc dot DOM, the scalar products with the elementary displacement, should be equal to 0, and hence, as I said, if you have two column vectors, basically the dot product between them is just not the simple matrix product. It should be the transpose of this times this, and since that gives you a vector, a row vector, and this a column vector, and then you will have a scalar which is equivalent to one number. Okay, so its transpose should be perpendicular to DOM, and hence it should its transpose should be a lambda times the Jacobian, and therefore the transpose of the transpose is just the identity. So we add another transpose on top of this, it just goes away. So Fc should be J transpose times a multiplier lambda, and this is called the Lagrange multiplier. You can Google it up to better understand this concept. I really don't like this notation. To better understand it, you should see J as a function. It's not a matrix, a static matrix. It's a function of x and y and z. So actually, I better understand it in this way. Suppose in this example, okay, we have a pendulum, and we want to see what are the forces that the system applies so that this constraint is always a constant, and this constraint, a squared plus y squared plus z squared, is equal to constant. It defines a surface in space in r to the power 3. It's this surface, it's the surface of a sphere. Now, of course, initial conditions should always satisfy your constraints. You should take initial velocities and initial positions such as the constraint is satisfied, and then you should advance the time step and see what are the forces that you should apply on the particle so it does not violate the constraints. Okay, suppose that we started here. The velocity, okay, we started on this point M. The velocity should be perpendicular, should be on this plane, okay? It should be tangent to the sphere. It should be a vector from this plane, and therefore the vector that defines okay, the vector that is perpendicular to all vectors on this plane is the Jacobian transpose, because as I said, I want column vectors, and Jacobian is just a row vector, so I take the transpose such that I have a column vector. Now this is the vector that is perpendicular to all velocities here, and since FC is perpendicular to our velocities, I mean, you shouldn't add power. Velocities can just be on this plane, they shouldn't really go out. This is impossible since it will violate the constraint, and therefore FC is just a multiplier times G transpose. Now why is J transpose perpendicular to this surface? Well, it's by definition df is just G times DOM. So if df is equal to 0, if this stays constant, so which means our elementary displacement is such as we stay on this isosurface, then J times DOM will be equal to 0, and that, since it's a row vector, means that J transpose scalar DOM is just equal to 0, which means that this is DOM and this is J transpose. You just give yourself some time to understand this pretty correctly. Just give yourself some time, Google Lagrange multipliers, and you will better understand this concepts. Okay, therefore we know that FC is just a multiplier lambda times GT. Now this is a simple case where C is just one scalar function. Of course, more generally it should be a common vector full of constraints, as we're gonna see in some examples. Of course, these are my examples. I brought this from Anjit great series, great channel, and these are the systems I'm gonna try to simulate. I'm gonna start maybe with this one and then move on to this one. As you can see, S is just full of parameters. This is a constant, this is a constant, but all of these are points that move. So yeah, S will be quite a big vector. Now this is the equation that we get. We substitute FC in this equation with J transpose times the lambda. The lambda is the multiplier that we're going to need. So in the case of a simple constraint like this one, a scalar one, lambda is going to be a scalar. But in the more sophisticated case of complex systems, etc., lambda will become a common vector with the dimensions of C. And then we need to solve this. I mean, this is a known matrix and this is a known matrix. This is actually a matrix, but more specifically it's a column vector. So a matrix times a vector is equal to another vector, and this is an eigen value problem, an eigen vector problem, valeur propre, vector propre. For those who did some linear algebra, you'll know how to deal with this. For those who didn't, it's really simple. It's just solving some systems of equations, linear equations. Now, and you solve for lambda, you find the vector, and then to calculate the force, you should calculate G transpose times the lambda. This is a matrix, this is a column vector, and the result is a column vector. Okay, we just understood how this works. Now, this is the equation that you need to do to find the forces, and you need some initial conditions, and that's it basically for rigid body simulation. The next video I will try and apply all of this to this system, and the results are quite good. Thanks for watching.